Okay, I want you to picture a scenario that sounds, frankly, completely impossible. Imagine taking an ordinary flashlight, turning it on, and shining that beam of light directly onto a solid piece of metal. Now, normally you'd expect the metal to just absorb the light, right? Maybe heat up a little bit. But instead, as the light hits the surface, the metal violently reacts and starts shooting out tiny, glowing electrons in every direction. I mean, it sounds like straight-up science fiction, but this exact phenomenon is absolutely real. Welcome to today's explainer, where we're going to dive into the photoelectric effect. This is literally the foundational experiment that completely shattered our understanding of light, matter, and the universe. To really grasp why this is so mind-bending, we have to start with a seemingly simple question. What actually happens when light hits metal? See, for centuries leading up to this discovery, the absolute greatest minds in science were utterly convinced that light was purely a wave. Full stop, nothing more. But when scientists finally observed this weird metal and light phenomenon in the lab, it completely destroyed that long-held belief. In fact, this single mystery was so profound that solving it gave birth to the entire field of quantum physics. So let's set the stage with Section 1, the Great Light Mystery, or when classical physics broke. Before the 20th century, scientists were absolutely positive that light operated as a continuous wave, kind of like ripples in a pot. And honestly, they had really good reasons to believe this. The wave theory perfectly explained almost everything they were seeing: reflection in a mirror, refraction through a glass prism, interference, diffraction, the whole shebang. Everything was tied up in this incredibly neat mathematical bow. So if we follow the classical view, a brighter, more intense light should naturally carry more continuous energy. Makes sense. So logically, if you shine a brighter light on a metal surface, that wave should eventually deposit enough energy to knock electrons loose. Simple. Except reality had other plans. That is emphatically not what happened. The rules of physics, as they knew them, were completely broken. Which brings us to Section 2, Free Shocking Discoveries. These were the clues that totally defied explanation. To figure out what was going on, scientists set up a highly controlled experiment. They put these perfectly clean metal plates inside a vacuum tube and started shining very specific different colored lights onto the metal. They fully expected that just cranking up the brightness would eventually release a flood of electrons. Instead, this vacuum tube became a full-on scientific crime scene. The results completely baffled the greatest scientific minds of the era. Here's what went down. Mystery number 1. When they shone a massively bright, intense red light on the metal, absolutely zero electrons escaped. None. They could wait for hours and nothing happened. Mystery number 2. When they used a super dim, weak ultraviolet light, electrons were immediately knocked out, like instantly. And then, mystery number 3. When they increased the brightness of the light that did work, the escaping electrons didn't get faster or more energetic, they were just more of them. Classical physics had zero explanation for this. It was a total breakdown of the existing theory. All right, Section 3. Enter the photon. This is Einstein's radical 1905 proposal. Someone desperately needed to rethink the fundamental nature of reality, and in 1905, a young Albert Einstein stepped up as the rogue detective to solve this impossible puzzle. He realized that to fix the problem, he had to completely throw out the assumption that light was strictly a continuous wave. Actually, he proposed a radically new version of reality. He asked, what if light doesn't just flow smoothly, but actually travels in tiny, discrete packets of energy? He originally called these packets light quanta. Today, we know them as photons. This was a monumental leap. Light, he argued, is fundamentally grainy. It's made up of individual, indivisible particles. And the exact amount of energy each one of these tiny packets carries is strictly determined by its frequency. The really elegant math behind this theory is perfectly summarized in this equation. E equals hf. Energy equals Planck's constant multiplied by frequency. This equation was the key that unlocked the whole mystery of the colors in the experiment. Because frequency dictates energy, higher frequency light, like blue or ultraviolet, packs a much bigger punch per photon than lower frequency light, like red. So red light photons are inherently low energy, while ultraviolet photons, those are basically high energy bullets. Moving right along to Section 4, overcoming the work function or the mechanics of escaping electrons. To really visualize how this solves our mystery, think of it like a cosmic game of billiards. Picture each photon as a tiny, highly energetic billiard ball moving at the literal speed of light. When one of these photon billiard balls strikes an electron in the metal, it transfers absolutely all of its energy in a single instant collision. So if you have millions of weak photons, like those from our blindingly bright red light,
It doesn't matter how intense that beam is, those weak photons cannot gang up or combine their energy to free a single electron. It is strictly a one-on-one interaction. But on the flip side, just one strong photon, like from our super dim ultraviolet light, transfers enough energy instantly to knock the electron completely free. But you might be wondering, why is there a threshold in the first place? Well, that brings us to the work function, which is represented by the Greek letter phi. Every metal is a little different, but they all hold on to their electrons tightly. The work function is basically the absolute minimum energy required to tear an electron away from that specific metal. Think of it as a physical wall. If a photon hits an electron but doesn't have enough energy to push it over that specific wall, the electron just falls back down. Nothing happens. But if the photon has energy greater than the work function, boom, the electron escapes. And we can actually track exactly where that energy goes with this beautiful little equation, K dot E equals HF minus phi. In plain English, the kinetic energy of the escaping electron is equal to the total energy of the incoming photon minus the energy it costs to get over that work function wall. Any leftover energy from the photon after beating the work function is immediately converted into the electron's speed, its kinetic energy. This equation perfectly mapped onto the results of that baffling vacuum tube experiment, completely validating Einstein's theory. Which leads us to Section 5, the quantum revolution, and how this built the modern technological world. By solving the photoelectric effect, Einstein proved an astonishing, mind-bending truth about our universe. Light isn't just a wave, and it isn't just a particle. It actually behaves as both. This wave-particle duality became the absolute bedrock of quantum mechanics, transforming physics literally overnight. And I really want to emphasize why this matters to you right now. This isn't just abstract chalkboard math. This discovery built the modern world. Because we understand how photons knock electrons loose, we can convert sunlight into electricity using solar panels. We can capture memories on digital cameras. We have automatic doors at the grocery store, fiber optic communication that powers the internet you're using right now, and space telescopes peering into the early universe. None of these technologies would exist without our understanding of the photoelectric effect. Okay, time for a fantastic cocktail party fact. The year is 1921. When you think of Albert Einstein winning the Nobel Prize, you almost certainly think of the theory of relativity, right? E equals mc squared. Well, surprisingly, that is not what won him the prize. In 1921, Albert Einstein received a Nobel Prize in physics specifically for his discovery of the law of the photoelectric effect. It was this work, confirming that light exists as both waves and particles, that the scientific community recognized as his greatest, most undeniable breakthrough at the time. To wrap up our explainer today, the photoelectric effect completely reshaped our understanding of reality itself. By simply trying to figure out why a piece of metal was spitting out electrons when a light was shone on it, scientists accidentally unlocked the quantum realm. It showed us that the universe is far stranger and honestly far more fascinating than we ever imagined. It really goes to show, sometimes the biggest revolutions begin with the smallest particles. Understanding the photon fundamentally changed our technology, our science, and our daily lives. But the quantum world is incredibly vast, and it is full of deep mysteries we are still unraveling today. So I'll leave you with this provocative thought to ponder. If a simple beam of light hid the profound secrets of quantum mechanics, what other massive revolutions are hiding in the smallest particles around us right now? Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.